This is Unit 4, Topic B, talking about the properties of the definite integral. Now that we've defined the definite integral as the area under a curve, there are certain properties that apply simply because that's what it is, because of the geometry of the situations. So for starters, if f of x is a positive function, always greater than 0, on the interval from a to b, then the integral from a to b of f of x dx simply is the area between the graph of f and the x-axis. This is nothing really new. This is exactly what we've been looking at. If we've got our function f of x, then between a and b, oops, that was a and a. Let's try a and b. That area is represented by the integral. So far, everything we've looked at has always had that area above the x-axis. The graph of f was always positive. If the graph of f is negative, that is below the x-axis, then what's going to happen when you do the integral is you're going to get a negative number. It's just going to be the opposite of the area. So areas below the x-axis essentially count as negative as far as the integral is concerned. So if I have my function f of x down here below the x-axis, between a and b, then that area, actually the opposite of that area, will be the integral from a to b of f of x dx. So in other words, the integral is going to come out negative whenever the area lies below the x-axis. All right, property 3. The integral from a to a of f of x dx is 0. Essentially that one I'm literally integrating from a to itself, and a straight line like that has no area. So the integral, the area of that line, would be 0. All right, this next one looks complicated, but when you think about the geometry, it's actually just common sense. It says if a is less than b is less than c, then the integral from a to c for our function is equal to the integral from a to b plus the integral from b to c. Geometrically, what we have going on here is if this is a and b and c, then the integral from a to b would be that part of the graph. And the integral from b to c would be this part of the graph. And all this is saying is that the integral all the way from a to c is the sum of the blue part and the pink part. Again, logically it makes sense. It looks a lot more profound than it really is. All right, the next one has to do with the direction of integration. We normally think of left to right as our positive direction. So if I integrate from a to b on a function like this that's above the x-axis, I will get a positive result. All this is saying is that if I integrate backwards from b to a, I'll get the same result, but opposite sign. It'll turn out negative. So there's actually two ways to get a negative value from an integral. One is if the area is below the x-axis. The other one is if you integrate from right to left, kind of backward from our normal order. These last two are arithmetic properties. And these are things that you've seen a number of times before in limits and in derivatives. And here they are again for integrals. It says that if I'm integrating a constant multiple of a function, it's okay to just pull that constant multiplier out in front of our integral, and I get c times the integral. Right? We saw before we can do that same thing with both limits and derivatives. This is the addition property. It says the integral of a sum of two functions. It's okay just to do the two integrals separately and add the result. And by the way, although I didn't write it as a separate property, this is also true for the difference of two functions. So plus or minus works. Once again, just like with derivatives, I'll have you note that what's not here is just as important as what is. Notice that there is no property that says the integral of a product is the integral of f times the integral of g, nor is there a property that says that the integral of a quotient is integral f divided by integral g. Those two cases we'll have to address later, and unfortunately you're going to find out that they're not nearly as nice as those situations with derivatives. There's no nice product and quotient rule for integrals. They actually turn out often to be very challenging integrals to do. All right, let's practice some problems based on these properties. So problem 1 asks us to find the integral from 1 to 4 of the function 2x dx. Since these are all geometric properties, let's look at the geometry of that. My function is just y equals 2x, which would just be a line with slope 2. So it would go through 0, 0 with a slope of 2. 5, 10 would be another point. It's going to look like that, right? And we specifically wanted the integral from 1 to 4. So that would be the area under this graph from x equals 1 to x equals 4. So my integral represents this area. Now, that is a nice area that just has nice straight sides, and we can find that area just using a geometry formula. That actually happens to be a trapezoid, right? Especially if I turn it this way, you might recognize the trapezoid. So that's just the area of a trapezoid. And again, you can either remember or you can look it up on your list of formulas. The area of a trapezoid is 1/2 times the height times the sum of the bases. And again, it might help us if we think about it this way. The height of this trapezoid here is 3. And the bases here and here. If we remember that this equation is y equals 2x, this point would be 1, 2. And this point would be 4, 8. So the y value 2 is the small base, and that y value 8 is going to be the large base. So if I put all that information into my area formula, the height again was 3, the bases were 8 and 2, half of 30 would be 15. So I know that the value of the integral is 15, simply because that's the area underneath that graph. All right, let's see if we can think about this next one kind of the same way. I know that I'm looking at the function the square root of 1 minus x squared, and I really want the area under that graph between -1 and 1. So let's see if we can sketch that graph. You may know what that one looks like, and if you don't, you can always use a calculator or Desmos to find it. This is actually the top half of a circle of radius 1. And let's see, let me use a zoom square so that we really see it looking like a circle. There it is. It's actually really tiny down there, but you can see it. There's the top or the semicircle of radius 1. And since I'm integrating from -1 to 1, I want all of this. So I'd have half a circle. And that means that the area is the value of the integral. A semicircle would be half of pi r squared. And the radius of this is just 1. So I'm going to end up with pi over 2 for the value of that integral, the area of the semicircle. All right, well, let's see. This is working so well. Let's see if it works for number 3. My function is x cubed plus x, and I'm integrating from -2 to 2. So let's go with x cubed plus x is my function. And I'm going to use a little bit smaller window this time. Let's just go from -5 to 5 on both axes. All right. Well, I may be in a little bit more trouble here because I definitely don't see a shape that I recognize. It's not a circle. It doesn't have straight sides. So let me sketch this and we'll talk about it, but I'm not going to get a for free area formula this time. Basically, the graph looked like that, right? Now I'm integrating from -2 to 2. So what I really am looking at is this area here and that area. This is the saving grace, right? I really don't know the value of either one of those areas, but by the symmetry, this one below the x-axis, which will count as negative, and this one above the x-axis that will count as positive, will have to add up to 0. They essentially cancel one another out because of the signs. All right, and the last one, this is an integral from 1 to 1. Doesn't really even matter what the function is. I know there's never any area from a limit to itself. So for sure that value is going to be 0. All right, let's try a few more. This time, I'm going to start you out with some integration values. So I'm just going to tell you the values of these 4 integrals. And I'd like us to use them to calculate the values of the remaining integrals, the ones that we're asked for here. So for starters, I want the integral from 3 to 6 of x squared dx. Now I'm going to notice that I do have 2 pieces of information about the integral of x squared dx. I know the integral from 0 to 6, and I know the integral from 0 to 3. So y equals x squared is just a parabola. Let's say this is 3 and this is 6. I've been told that all the way from 0 to 6, so this entire thing, has an area of 72. Right. I also know that the part just from 0 to 3 has an area of 9. So this part has an area of 9. That means the part that I want from 3 to 6 is just going to be 72 minus 9. Or 63. All right, what about number 2? For this one, I'm actually going to get out the arithmetic properties, those last couple on our list. And I'm going to say I could rewrite this as, first of all, these are all added and subtracted, so I can separate out all the terms and do it as 3 separate pieces. And in my first piece, I'm going to take that constant 2 and bring that outside the integral, constant multipliers. I'm allowed to do that. And then that just becomes 2 times the integral of x squared dx. Next one, I've got a multiplier of minus 5. So I'm pulling that 5 out in front again, and then it just becomes the integral of x dx. Plus, and I'm going to do something kind of similar here. That 4 is a constant multiplier. If I brought that constant multiplier out in front of the integral, 4 divided by 4 would leave 1 inside. So all I've done there is split this up as 3 separate terms, 3 separate integrals. And in each case, I've taken the constant multiplier and brought it out in front of the integral. Now I can fill in some values that I was given. The integral from 0 to 6 of x squared dx, that one's 72. Minus 5 times the integral from 0 to 6 of x dx, that one's 18. Plus 4 times the integral of 1 from 0 to 6 is 6. So if I just go ahead and run that on my calculator, I get 78 for the final value of that whole integral. All right, number 3. The integral from 3 to 0 of x squared dx. This one looks a little funny to us because we're always used to seeing things from the smaller number to the larger number. This is that backwards, integrating from right to left instead of the usual left to right. And we know all that did was change the sign. So this is the opposite of the integral from 0 to 3 of x squared dx, or minus 9. And then the last one, our favorite one, if we're going to go from 3 to 3, there's no area enclosed. So definitely the value of that one's going to be 0. All right, nice short section for a change brings us to the end of topic B.